These slides give an introduction to linear time periodic systems. Linear time periodic models are appropriate for a wide range of systems. Some of the most common examples are rotating structures such as a wind turbine. You can see this very easily with a one-bladed wind turbine. Imagine the turbine when the blade is in this configuration, where we have flexibility in the blade and in the tower. At an angle of 0 degrees like this, the blade would bend in the vertical direction and it would pull axially on the towers. There'd be very little contribution there. And the stiffness of the tower wouldn't really enter in. In contrast, if the blade was at 90 degrees and vibrates again in the same direction relative to the blade, there you would have a strong coupling with the bending of the tower. So in this case, the total stiffness, due to a force applied at, say, the tip of the blade, would be lower. What that causes in the end is the stiffness of the system overall to change with angle, or if the rotation speed is constant, to change with time. And so that is one common example of a time periodic system, though this type of model is appropriate for any nonlinear system when we linearize about a periodic limit cycle or a time-varying limit cycle. Other examples of nonlinear systems, orbital mechanics, satellites or moons traveling around planets, comets, things like that. Those gravitational fields are nonlinear, but if we linearize around the periodic orbit, we can understand interesting things about the system, such as how that orbit will evolve with time, whether the orbit is stable to a perturbation, and so on. Similarly, in biomechanics, a walking or running human is a highly nonlinear system, but if we are interested mostly in how stable that walking is or how the walking might evolve with time, we might use a time periodic system and think of small perturbations from the average stride. We've also used these techniques to speed up measurements, as I'll talk about in a minute. We've also used these techniques to speed up measurements and to perform measurements and operational modal analysis on wind turbines. This area started to pick up. For example, just a few years ago there was a keynote at the International Operational Modal Analysis Conference related to wind turbines and how the time periodic system techniques that we'll talk about here apply to those structures. So why should we care about time periodic behavior? Well, it introduces some significant complications in the response of a system. And most importantly, it can change the effective damping in the system so that the system becomes unstable. For example, this plot shows a time periodic system, a 1DOF system that we'll talk about later, called the Mathieu equation. And it's linear and time invariant except for this stiffness here, which changes with speed. And if we plot solutions of the system versus the speed of the stiffness pumping, the speed with which the stiffness changes, we see that the effective damping changes dramatically at certain speeds. Now, if this was a time invariant system, we'd expect that damping to be constant, and you can see that in some cases we'd be dramatically wrong. If we thought, for example, the damping was positive when it's actually negative at this rotation speed, we could completely underpredict the vibration response and lead to failure of machines. So this type of analysis is important for turbines, any kind of rotating machine. It's done all the time for gearboxes and transmissions and automobiles and airplanes and other structures like that. This time periodic behavior can also just lead to confusion. For example, say we are thinking about the forced response of a system. A time invariant system, when forced at a single frequency, will give a response of that same frequency simply with a change in the magnitude and phase. In contrast, a time periodic system, when excited at one frequency, will respond at that same frequency, but also at other frequencies spaced by integer multiples of the rotation frequency from that. And so this can lead to exciting a resonance even if the forcing is away from resonance. For example, if we excite at this frequency, the second harmonic might line up with resonance and still cause a much larger response than expected. So one of the main reasons that we build wind turbines with 3 blades is the fact that that avoids this time periodic behavior. By building a turbine with 3 blades, and if the blades are all identical, we can approximate the turbine the rotor as a whole, as an isotropic kind of disk. And so there's little concern for time periodic behavior of the turbine unless we have damage to a blade or the blades are different due to manufacturing defects and tolerances, which, by the way, they always are. But if we were to understand and exploit this type of behavior, then it becomes possible to design a turbine with 1 blade or 2 blades, and understanding its response, design it so that it doesn't have unwanted resonances. We've also used this technology to accelerate mode shape measurements. In a typical modal test, we apply a force and we measure the response at a single point, and then a second response at an additional point, and then we might repeat that again and again at many different points to collect the mode shapes of a structure. If the structure has low natural frequencies or is lightly damped, each one of those measurements can be really long. One alternative is to use a laser vibrometer and scan that periodically over the surface of the structure. These pictures here show a laser being scanned. Actually, look, you can just see the laser line painted on the wind turbine blade. So in 2 measurements, we could acquire data where the laser is visiting all the different locations on the blade. Now the challenge is that the model for the structure then becomes linear time periodic, so we need to understand the theory behind these systems to be able to make sense of the measurement that we get. But once we do that, we can take 2 measurements such as these and use that to reconstruct the deformation shape of the blade, whereas a conventional measurement may have taken 40 measurements or more to get this same kind of resolution. So in other words, 20 times as long. And if each one of those measurements is 30 seconds or 1 minute, that time starts to become appreciable. Or if we're talking about a full-scale wind turbine, we might need 15, 20 minutes, half an hour per measurement. And so the time becomes very, very long. Okay, and all this can be done with linear time periodic system theory. You can look later at this slide, which describes the notation that we use in these slides. And here's a bibliography with some good papers on the subject, mostly focused on the work that our group has done in this area. Let's jump right in and start talking about the response of linear time periodic system. We'll cover vibration of single degree of freedom time invariant systems to set the foundation for this, and that will serve as a springboard into time periodic system theory. I'll skip over most of this. I think you can read through these slides on your own. They talk about the relationship between traditional mass spring damper models and state space descriptions. And also a review of the free response of time invariant systems. The moral of the story here is that if we start with a 1DOF system free response, that we can write the free response as a sum of sine and cosine multiplied by a damping term. That becomes even simpler if we go into the state space, where we can then simply write the response of the system as a sum of a constant times an exponential e to the lambda t. For a 1DOF system, we have 2 states, position and velocity, so we have the sum of 2 exponential terms, which are complex conjugates. Okay, so one concept that we'll need to understand time periodic systems is the state transition matrix, and we'll begin talking about it and review how it would be used for a time invariant system and use that as a springboard into time periodic systems. So the state transition matrix is a matrix, a time-varying matrix. It depends on the initial time and the final time, that when multiplied by a vector of initial conditions produces the response at a later time. So this state transition matrix transfers the system from the state at time 0 to the state at time t. So once we've found the state transition matrix for a system, in essence we can write the transient response down analytically. A simple example, if we go back to our undamped 1DOF system, we derive that the time response was this, the initial displacement times a cosine omega t, and then initial velocity times a sine omega t term. If we just take the derivative of that equation and then rewrite it to factor out the initial displacement, initial velocity, we can write it like this. And immediately you can identify the state transition matrix as this matrix right here, because given an initial condition, we multiply this matrix by this matrix to get the response at any time. Now this state transition matrix has a lot of interesting properties. There's a differential equation that we can use to solve for it in general, and it has to satisfy this initial condition. And you can see that immediately from this equation, that if we start at time t0, then the state transition matrix from t0 to t0 has to produce the exact same initial state, so it has to be an identity matrix. Another interesting one is the semigroup property, or in other words, if we want the state transition matrix from t0 to t2, that's simply the product of a matrix that takes us from t0 to t1 and another one that takes us from t1 to t2. And again, you can see that immediately in this equation if we see how the multiplication of this matrix takes us from one time to another. You can then also show that to go backwards in time, we simply switch the time arguments. Or in other words, the inverse of the state transition matrix is the matrix with the time arguments switched. Okay, so you can find more information on these in a good text on modern control theory, but that covers enough for our purposes. So how do we find the state transition matrix? Well, if we know the analytical solution, as you saw earlier, it's easy to write it down. Some controls books cover Laplace transform methods. For our purposes, the most interesting method is the matrix exponential method. Or in other words, the state transition matrix is simply the exponential of the state matrix times t minus t0. And first, since we're talking about time varying and time periodic systems, I need to warn you that this equation is not valid for a time varying a of t. We can't simply plug in a of t and get the correct answer. But this is useful for time invariant systems. It might be helpful to review what we mean by the exponential of a matrix. You could work this out using the Taylor expansion formula for the exponential and see how this works. Or using a modal decomposition, one could show that the state transition matrix is just the eigenvectors, an exponential of each of the eigenvalues times t minus t0, and then the inverse of the eigenvector matrix. If we write this instead in a summation form, where we take each column of the mode matrix, each eigenvalue, and each row of M inverse, we can write this in this form where the time response just becomes a matrix of constants, E times e to the lambda t, and then we sum up over all the different eigenvalues. Where this matrix is a rank 1 matrix, actually it's a vector in this case, it's a product of a rank 1 matrix, which is the eigenvector and the row of the inverse of the eigenvector matrix, and the initial condition vector. So the response of the system we can see again is just a sum of constants e to the lambda t. And we can see that from the state transition matrix or from an analytical solution that we might have worked out a different way. And this slide just emphasizes the fact that for the SDOF system we saw that the response was a sum of eigenvalues times constants, and that's exactly what we got for an arbitrary linear system in general. So this underscores the importance of the eigenvalues in understanding what the response of the system will be. And for a time invariant system, those eigenvalues are the eigenvalues of the state matrix A, but notice they're also the eigenvalues of the state transition matrix, or they're related to the eigenvalues that we would get if we diagonalize the state transition matrix. Okay, so in general, how could we find the state transition matrix? Suppose we have a time-varying system with a state matrix A of t. There are analytical solutions that are available, but very few for the problems that we might be of interest analytically. So typically we use numerical computation. One simple way to do this is to compute the response of the system to an initial condition where one of the states is 1 and the rest are 0. We repeat that n times, where we alternate which state is given a value of 1, and we collect those into a matrix. And then, since the initial condition matrix is an identity, that matrix of responses is the state transition matrix. Because the system is linear, if we multiply by a vector of responses, we will simply scale each of those solutions to the initial condition, and we immediately produce the response. So this is a powerful approach, and it can be done very cheaply. And actually, there are improved algorithms. A paper by Friedman in the 70s showed that you could integrate the system in a single pass using an algorithm like Runge-Kutta that would produce the state transition matrix in a single pass by basically integrating the equations with an identity matrix as the initial condition rather than a vector initial condition. Okay, so let's also review quickly the forced response of time invariant systems, and we'll see how the state transition matrix can actually be used as an alternative for finding the forced response. So from an undergraduate course on vibrations, you might remember that the forced response of a time invariant system is found, well, the forced response has two parts, a steady state term and a transient term. The transient term is simply the term that we found earlier for an unforced system. To get the steady state response, we assume that this term has vanished, and so we simply plug an assumed form for the steady state solution, which matches the form of the forcing, into the equation. We solve for the amplitude and phase, and using the complex exponential representation, we can pretty easily come up with this expression for the complex amplitude of the response as a function of the complex amplitude of the force. So all of this is done very easily through algebraic manipulation for a time invariant system. And this gives rise to the traditional resonant behavior that we see for a 1DOF system. As the response frequency, as the forcing frequency nears the natural frequency of the system, we see that the stiffness and the mass terms cancel, and we're left with only the damping in the denominator. And so we can get a large amplification of the resonant response as we force near the resonant frequency. Okay, now it's important to note that we could also find the same result using the state transition matrix. Standard text on controls would derive this equation, which explains how we can find the response at any time due to an initial condition and a forcing function u of t. We have a transient term, which we've already talked about. That's the initial state times the state transition matrix. And we can solve a convolution integral to find the forced response of the system. So once we know just the state transition matrix and the other system matrices, we can simply evaluate an integral to find the response to any forcing. So this doesn't require the traditional time integration approach. It's just a simple convolution integral. Let's do an example. Consider the 1DOF system that we talked about earlier. This was the time-invariant 1DOF system state matrix, the A, B, C, and D matrices. And we found earlier that its state transition matrix was given by this analytical expression. So if we want to use that to find the force response, we'll leave off the transient term for now, even though technically that term would never disappear. Let's focus on the steady state term. Plugging everything in, we end up with this integral, which we could evaluate to find the forced response. Using some trig identities, we can eventually write that this way. And the important thing to note is that this equation tells us exactly what we saw with the analytical approach, in that as the forcing frequency comes close to the natural frequency, this term will get a large integral as time goes towards infinity, because the area will always be positive, the area under the curve will always be positive, so the longer we integrate in time, the larger the amplitude of the response. So that shows why an undamped system has an infinite response as t goes to infinity. So this isn't nearly as elegant and clean as the conventional approach, right, where we simply get a nice expression for the complex amplitude of the steady state response. But we see that it is possible, and that'll be important for time periodic systems where it's not so straightforward to write the analytical solution, the complex amplitude of the analytical solution. Okay, now we've covered enough that we're ready to move on to linear time periodic systems. Let's start with free response. Have a simple example, as we go through these examples, let's consider the Mathieu equation, which is the equation of motion for a single degree of freedom time periodic system, where the mass and damping are constant, but the stiffness is a time-varying function of time. So there's a period with which the stiffness is pumped. The stiffness has a constant term plus an oscillating term with a coefficient beta. So notice this isn't a forcing at all. This is simply saying that the stiffness of this spring changes with time, its resistance to deformation. But we'll see that that ends up leading to all kinds of interesting response. For example, we'll switch over to MATLAB quickly, and this script, which you've been provided, will integrate the equation of motion of the Mathieu equation, given a certain set of parameters, mass, natural frequency, and stiffness, and a damping ratio. Let's start by setting beta to 0. We'll get a traditional 1DOF system. And this will then, the frequency with which we pump the stiffness then becomes irrelevant. And I'm applying an initial condition of 0.9 and 0. So an initial displacement, 0, initial velocity. Oops. And let's run both of these cells. And this is the free response of the system. And again, it's just a linear time invariant system, so nothing really interesting happens. What happens as we begin to add time periodicity to the system? Initially, with this particular setting, we don't see anything too interesting. If we looked really closely, we might see some distortion in the response, but it's still stable. Nothing too crazy has happened. If we change the frequency with which we pump the stiffness, we start to see a little more interesting responses. Here you can start to see a little bit of a beating, or in other words, this time periodic system has responded at more than just the natural frequency. So there's more than one response frequency in the system. We'll just try one other case. As you go towards the resonant case, though, that becomes a little less visible. So as we increase the strength, though, of that pumping term, or the strength with which the stiffness varies, for a wind turbine, this would correspond to making the blades more different in stiffness, or the blade plus tower stiffness changing by 40%, or actually by 80%, because there's a 2 beta in the equation. In any event, as we go to that case, we look at the transient response, and now we see, given a small perturbation, the response is actually growing exponentially with time. So the system has gone unstable and the wind turbine comes crashing down. So if your system can exhibit this type of behavior, it's definitely something we'd like to know about. We can understand the transient response using a state transition matrix, which I haven't told you how we'll find yet, but we can actually solve for the state transition matrix. Notice, though, because the system is periodic, that if we want the response in an arbitrary time, say 1 period later plus some fraction of a period, we can get that by starting at time 0, multiplying by the transition matrix from 0 to the end of the period, and then from the end of the period to time t. In other words, what we get is this equation right here. So this matrix concerns with a fraction of a period, and this one with 1 integer period. Now, for a response at any time t, we just generalize that by counting how many cycles the system has gone through, how many periods. And the response is then just the state transition matrix for p periods to the pth power, or for 1 period to the pth power, and then the small transition matrix from the end of the period to the time of interest. So we're raising a matrix to a power, so clearly this is the matrix that will govern the response, that will be critical to understanding how the system responds. And in Floquet theory, this matrix is called the Floquet transition matrix. It's the state transition matrix over 1 period of the system. And its eigenvalues will be called the Floquet multipliers. And we'll see later that they govern the stability of the system, similar to what you might see if you take a class on discrete control, where you have a similar relationship. In discrete systems, we say that the response at some time is a matrix times the response at the previous time step. And so this matrix power, we take this matrix to powers as we march forward through many time steps. The same thing is happening here. And so if the eigenvalues of this matrix have a magnitude greater than 1, we'll see the response diverge, and we get exponentially growing solutions. Okay, so to understand this, let's think for a minute only of response measured at integer multiples of the period. So in that case, the response becomes very simple. It's just governed by this matrix to the p power. As time increases, p increases. So if we solve an eigenvalue problem using this matrix over just 1 period, we can find its eigenvalues, which we call the Floquet multipliers, and its eigenvectors. And then we can diagonalize that matrix. As a result, this equation simply becomes the eigenvector matrix, a diagonal matrix of eigenvalues raised to the p power, and then this matrix again, the inverse of it, and the initial condition. Or in other words, we see now why those eigenvalues need to have a magnitude greater than 1. If they're or less than 1. If the magnitude is greater than 1, these terms will diverge. with time, and the system is unstable. We could also write those Floquet multipliers as Floquet exponents. We define those as the natural log of the Floquet multipliers. Or in other words, we have this relationship. And so now we can then write this in the same type of form we have for a time invariant system. So the stability is governed by the eigenvalues, Floquet exponents, lambda, and PTA becomes just our time term. And so with this description, the Floquet exponents are like traditional time invariant eigenvalues. If their real parts are positive, we have instability. If the real parts are negative, we see damped responses. So this one matrix governs the response of the time periodic system. Again, this slide just summarizes the relationship between Floquet multipliers and Floquet exponents. Okay, so how do we compute the Floquet transition matrix? Well, once again, the best way to get it, since there are so few analytical solutions available, is to integrate the equation of motions in times with indifferent initial conditions. Because the system is periodic, we only need to do that over one period, which often is quite short relative to the time span of the responses that we might be interested in. But from the state transition matrix at that one period, we can evaluate the response over any time period. So we find the Floquet transition matrix, we find its eigenvalues, and then we know that the system is stable if those eigenvalues have magnitudes less than 1, or we can calculate the Floquet exponents and see whether the real parts are less than 0. We could also define an equivalent damping ratio and see whether the damping ratios are all positive. So this is implemented in a script, which I'll show you quickly here in MATLAB. The same script we were using a minute ago. Here I've defined the time invariant state matrix, and I've defined the equation of motion with a time varying state matrix right here, governed by the pumping frequency omega A, which I call OM here. So basically I just wrote a loop, and for every possible pumping frequency of interest, I'll integrate the equation of motion from 0 to the end of a period, subject to an initial condition 1, 0, 0, 1. If we collect both of those responses into a matrix, we get the Floquet transition matrix, and then we can find its eigenvalues and store those and plot those. So here are some examples of calculations from that script. First, we look at a case where we have fairly light variation in the stiffness. So the stiffness is changing by about 40% over one cycle. And we have fairly light damping, but not extremely light. And if we look at the Floquet multipliers of the system, we see that as the rotation frequency increases, we get some blips. The most important one is this one, where the Floquet multiplier, one of the Floquet multipliers becomes greater than 1. So the system is unstable in that frequency range, in that pumping frequency range. Again, we're not forcing the system at all. We're simply looking at transient responses as a function of the frequency with which the stiffness varies. So this is an intrinsic property of the system, that it's inherently unstable if we pump the stiffness at a certain frequency. And this is the case for beta as 0.2. An alternate way to view that, for those of us from the structural dynamics world, is to think of it in terms of damping ratio. So we plot the damping ratio of the system versus the pumping frequency. And it's counterintuitive that the frequency with which we change the stiffness affects the apparent damping, but it does. And so there are many different speeds with which we might pump the stiffness that lead to instability or that lead to changes in the damping ratio. And at low pumping frequencies, actually these are mostly beneficial. In other words, the damping ratio, the effective damping goes up if we pump the stiffness just right. However, if we pump the stiffness quickly, we see regions where the damping goes negative and the system goes unstable. As we make the stiffness variation larger, we get larger regions of instability and more of them. So you can see from this plot how we might design a time periodic system either to be beneficial by increasing damping, but it can also be detrimental if we don't understand it. Also wanted to note that this is a general rule that just as you think of forcing a system at its resonance frequency to get the largest response, with a time periodic system, if we pump the stiffness at twice the natural frequency of, say, the linear time invariant part of that system, that tends to be when we see the worst case instability. So here our natural frequency was 1, and we get a small instability there, but the big one occurs when we pump the frequency of the stiffness twice as fast.